opportunity to speak here. I feel somewhat out of place as an algebraic geometer, and I'm going to talk about things that I find interesting, and I hope you find them interesting too. If you say you know all of these things, this is silly, you're saying things in a different language, please come talk to me after the talk and tell me all you have to know. So this is based on work in two projects, one with Madeline Brand, Steinberg, and Corey Wolf, and one with Iran Hassa, Madeline Brand, Chan, and Luca Vlad. And I've done the hard part of writing all my co-authors on the board once, so I don't have to do it again. So I will just refer them by various long lists of acronyms. So my kind of connection, I would say, to being here is that I'm interested in studying the cohomology of various moduli spaces, which in essence means studying homology of various arithmetic groups. So to begin, in the title, the main player is Shimura varieties. So what is a Shimura variety? The definition is that Shimura data, or datum, is a pair G comma D, where G is going to be a semi-simple group, algebraic group, defined over the rationals, and D is going to be a locally symmetric Hermitian domain. I'll give examples of these two things in a moment, and we want to have some interplay between the group G and the domain D. So what should you be thinking about D? D is essentially a locally symmetric space that has an almost complex structure, and the connection is that the real points of G should essentially be the automorphisms of D. So the connection is we're also in this data, although I won't reference it, fixing an surjection from the automorphisms of D onto from the real points of G. And I want to fix this surjection so that it has compact kernel, and so that if I call this group G, so G is always the real points of that black hole over G, then we get that D is actually isomorphic to G mod some maximal compact group. So this is the main player, and then from this data, if you give me gamma an arithmetic subgroup, of, let's say, G, I just want to say arithmetic subgroup of GQ, then we can form X being the quotient of D by gamma. And this is what we call a Shimura variety. Okay. And so this is, a double quotient of some real Rayleigh group G by a compact and then an arithmetic group. So these appear all over the place. And as the name might suggest, this is in fact not just some topological space, but is an algebraic variety. So Bailey and Burrell showed that X has the structure of a complex quasi-projective variety. So locally it looks like something cut out by polynomial equations over C, and then right around the same time, and the literature gets confusing, Shimura, hence the name, showed that not only are these things defined over C, but in fact you can find nice canonical models over number fields for these things, where which number field you have to take depends on the datum you fix. Okay. And for me, these are going to be the main players in today's talk. So let's look at some examples to make sure we're all on roughly the same page. And there's going to be 3 examples that I want us to focus on. In the first example is what I'm going to call AG. And I write it as AG because for an algebraic geometer, I would call this the moduli of abelian varieties of dimension G with principal polarization And so in this case, our group G is going to be the symplectic group of size 2G. Script G is just going to be the real points of the symplectic group, so it's the real 2G by 2G matrices that preserve some symplectic form. And if I don't reference the symplectic form a priori, I'm just going to be taking the standard one, which is identity, negative identity on the off diagonals, zeros everywhere else. So here we get this, and then you could check that my domain D is going to be what's known as the Siegel upper half plane, which concretely is going to be the set of G by G symmetric matrices defined over the complex numbers, such that if I take the imaginary part of this matrix, it's positive definite in the sense that Zach so kindly defined yesterday, so this is some quadratic form. It takes on positive strictly greater than 0 on all non-zero vectors. So you can check, right, that D is in fact going to be the quotient of sp2gr by the unitary group. And in fact, all you have to do is check what the kernel is over any given point. And we could now choose basically any arithmetic subgroup inside of G we wanted. But in this case, to get the moduli of abelian varieties, I would take gamma to be sp2gz. And so if I look at sp2gr mod sp2gz, I get what an algebraic geometer would call the moduli space of abelian varieties. So this is the first example.
What does it make? What does make D Hermitian? What does it mean to be Hermitian?
So being Hermitian just means I have it's a locally symmetric domain with an almost complex structure. So if you want, you can think about this as being inside the space of all kind of complex matrices, and it has some complex structure that's compatible with respect to the nice action of the unitary group. Does that answer your question?
Not really, but I don't think it's answerable with my knowledge, so I will
we can talk later.
keep going.
Can I ask a terminology question? In this definition, X is the Shimura variety, even though X wasn't part of the what you call the Shimura datum?
Yes. Great question. I don't know why people do this. I'm also not an arithmetic geometer, and so people often talk about the Shimura datum G comma D, and then you define the Shimura variety by then further specializing a choice of arithmetic subgroup. And I think
that's what I'd call a locally symmetric variety. There's more information in Shimura variety. For example, it's a map of the Deligne torus.
Yeah, so often
into G or something.
That's great. So oftentimes people will look at extra data here, and so maybe we'd only want to call this a locally symmetric variety, and we'd want to also fix extra datum to look at the Shimura variety. Often Shimura varieties, when you're looking over kind of the number field place, will be a union of locally symmetric varieties. Since we're only going to work over C, it's going to essentially just look like this connected component.
So maybe one comment. I don't know if I'm getting too out of, but one Shimura datum doesn't just give rise to one Shimura variety, but a whole inverse system of all of them.
Yes.
And often you study them together.
Yes. So that was the next point, is that example 2 of a Shimura variety.
Could I?
Yes.
Follow-up question to Peter's maybe before I get to the next.
Yes.
Sorry, I didn't want to interrupt, but could you maybe just say for a type of group where you have where it's an Hermitian, where this locally symmetric space is Hermitian, and one where it's not? I mean, okay, there it's Hermitian, but I guess this is with the direction of Peter's.
Okay, so a locally symmetric space that isn't Hermitian, take the positive definite cone of real matrices and
okay, so SL wouldn't work and SP would. Okay.
And take the quotient by GL, right? That's the.
Isn't this even symmetric domain? I mean, no.
Yes. So locally, this right here.
No, the D.
Yes, D is a locally symmetric domain. It just has.
Not just locally symmetric, right?
Yes. In this case, is also.
Okay.
Symmetric, yes.
No, I don't know. I don't know this, like what these words actually mean, but I just usually hear, like D is the symmetric space, and then mod gamma is the locally symmetric space. That's the terminology that I've always heard. I was just wondering. I don't know what the words actually mean. So
I will
that's
say
fine.
this terminology seems to get used slightly differently in about 3 to 4 different fields, and so I apologize in advance that So the first example is AG, and the second example, as Dan suggested, I'm going to call AGM, and brackets here. And in this case, G, G, and D are exactly the same as before. So this doesn't go up. So G, G, D as above. But now I take gamma to be some principal congruent subgroup of sp2gz. So just the kernel of the map from sp2gz to sp2gz mod mz. So this is some nice arithmetic subgroup of sp2gz, and if I take the quotient of this same space here, hg, by this gamma now, I get, in fact, what we call the moduli of abelian varieties with level M structure. And in fact, as Dan was suggesting, this somehow comes together with this in that AGM is a cover of AG. And so as M varies, we get kind of a family of covers one could study all at once and ask questions about things of, how high in the cover do you have to go before you get nice properties. So these are the 2 main examples I want to have in mind. I will note, it's not so important, but when we say level M structure, essentially I'm saying I'm adding extra markings to my torus, namely I'm remembering some special isomorphism between the M torsion of my abelian variety and a fixed reference M torsion. So these are the first 2 examples. Let me do one more.
And instead of the principal congruent subgroup, could you just take any finality?
You could take any congruent subgroup, yes.
Oh, it has to be a congruent subgroup. Can't be.
I mean,
just
it could
a
be any
random-
arithmetic subgroup,
Yeah.
but I think all arithmetic subgroups are principal for sp2gz.
They're all congruent subgroups.
I am not so brave in my group theory to venture outside the land of principle. Okay, so the third example is slightly more exotic. So it's APQ. I have 2 numbers, P and Q, and now I'm going to fix E. And what is E? E is going to be some imaginary quadratic field. So say Q adjoined square root of minus D. My group G is somewhat weirdly going to be the special unitary group size P comma Q over E. So this means I have some form. The form J concretely looks like minus identity Q, and then some matrix S that I get to fix the datum of in this choice of form. So this is my group here, and when I say E here, I mean if I gave you an input A, you need to tensor E by A to evaluate this group at the A points.
Sorry, where's the P show up in this?
The size of this. So this should be a P plus Q by P plus Q choose
And
matrix.
there's no other conditions on S other than just
Not really. Not that there are some technical conditions,
Okay,
but
that's-
not
yeah.
worth going into.
Yeah.
And then, as before, you could in fact say that G is just going to be, some subgroup of this, the real points of this group. And somewhat weirdly, since E is an imaginary quadratic extension, when I evaluate on the real points, I'm actually looking at the complex points of this form. And so you could think about this concretely if you would like, being the elements in SP plus Q, sorry, SLP plus Q of C, such that X preserves the form J. So somehow when we evaluate on the real points, we actually get a very concrete description of what our group is. D is going to be pairs WZ, where this lives in, this is, the first matrix is a Q by Q complex matrix. The second matrix is a P minus Q by Q matrix, padded together into block form, satisfying some imaginary part is positive definite. So I'm being somewhat vague with the definition of this. It's a bit tedious to write down, so apologies, but to give you a sense that there are slightly more complicated structures here. And lastly, well, what could you think is your arithmetic group? In this case, gamma is SUPQ of my ring of integers of E. So here, this is integers for E. In fact, you could take some order in the ring of integers if you would like, but let's not do that now. And so once you take the quotient of D by gamma, you're going to get a space that I'll call APQ of E. And essentially this parameterizes complex abelian varieties, or abelian varieties with complex multiplication by O of E, together with some additional data about the pairing on the Lie pairing here. So somehow you can remember more. Somewhat strangely, maybe, I've had 3 examples, and I called them AG, AGM, and APQE. And the reason these all have this name is because often Shimura varieties are what we call Hodge type, which means they parameterize exactly abelian varieties with extra Hodge type data. And so the nice thing about these sorts of varieties, and Shimura varieties in general, is that, well, the action of gamma on D is properly discontinuous, and the stabilizers are going to be finite. And so if I'm interested in looking at the cohomology of X, say with rational coefficients, this is the same as looking at the group cohomology of gamma with rational coefficients. So anytime I'm looking at cohomology of Shimura varieties, so when I'm looking at the cohomology of AG, AGM, APQE, I'm secretly studying the group cohomology of the arithmetic group gamma. So if you had questions about SP2GZ, you could look at the cohomology of AG. If I'm studying the cohomology of AG with level structures, I'm studying the group cohomology of congruent subgroups. Here I'd be studying cohomology of special unitary groups with quadratic rings of integers. And for me, studying the cohomology of these spaces is just very natural. These moduli spaces have appeared in algebraic geometry since the time of Riemann, but I want to suggest that also the fact that we are allowing to look at this space that is an algebraic variety endows the cohomology of X with extra structure that I don't think you would necessarily see if you just approach them from studying the arithmetic groups on the nose, at least my understanding of them. In particular, we have, for any variety X, the cohomology of X carries extra structure. So if X is a variety, and then I look at the ith cohomology group of X with rational coefficients, it turns out that work of Deling implies that this doesn't just come to you as a cohomology group. There is a mixed Hodge structure on this. So in particular, I get an increasing filtration of this group. So you have an increasing filtration, W naught of HI plus. And not only do we have an increasing filtration, we know the filtration ends at step 2i, where I is the cohomological index, and we call this filtration the weight filtration.
Since X is smooth, it will start at Wi.
Yes. So if I assume, in these cases, since X is smooth, at least it's a stack, I can start at I. Just in general, I have a variety. Things could be.
Superscript instead of a subscript?
Here? Sorry. That was just a typo. Thank you. And the reason this is nice is it opens up the tools of Hodge theory to us, but also it allows us to look at smaller pieces of the cohomology of X over the cohomology of gamma. In particular, instead of having to try to compute kind of all of this at once, we can focus on individual pieces. And so whenever you have a filtration, we can look at the graded piece. So let's define the jth graded piece as HI of X. And do the quotient of the jth graded piece in this filtration by everything lower. And this is what we call the jth graded piece of the cohomology in degree I. It turns out this carries a natural pure Hodge structure of weight j. So essentially it says this quotient looks like the cohomology of a smooth projective variety, even though a priori X may not be. It will be when we're in Schmerber variety land, but it won't always. And in fact, this is quite a nice natural filtration in that it's compatible with things like Poincare duality. So if I assume X is smooth, smooth and separated if I want to work up above more stacks, then we get, if I look at the weight j piece of the ith cohomology of X, with rational coefficients, this is isomorphic via Poincare duality to the weight 2d minus j h 2d minus I cohomology of X comma Q. If I take compact support, where d is the dimension of X as a complex variety. So twice d would be the real dimension of the space. And I have to take complex or compact support here because in general, my algebraic varieties, in particular almost all of these Schmerber varieties, will not be compact in general. To make a Poincare duality, we have to add compact support. And a thing you notice immediately from this is, well, if j is bigger than 2d, this right-hand side is negatively weighted, and that doesn't work with the filtration. So in some sense, gr 2dw of hi of X, which is isomorphic to the weight 0 compactly supported 2d minus I homology of X, is what we call the top weight slash weight 0 piece of X. So in some sense, this is a nice thing because this is a canonical quotient of my cohomology group HI of X. So in particular, if the top weight cohomology here is non-zero, it implies my original cohomology group of X is non-zero. So non-vanishing of top weight implies non-vanishing of cohomology. And likewise, if you prefer to work with sub-objects instead of quotients, you could also work compactly supported cohomology, and weight zero compactly supported cohomology being non-zero also implies the corresponding.
You ended the weight filtration at I for HI.
Yes.
So that means that if I is smaller than D, then this has to be 0.
Yes. Okay. So in particular, when I is small relative to D, we kind of can't see top weight cohomology in particular. Okay. And so the entire point, I would say, about, well, the title's now gone, about tropicalizing varieties is trying to find ways to gain access to looking at these particular pieces of the cohomology of my algebraic variety. And ideally doing this in some nice way. So somehow, right, the goal maybe would be to find a way to compute the top weight cohomology of AG, or AGM, or APQE, because if we can compute classes in top weight of any of these things, we will have produced classes in the cohomology of SP2GZ, congruent subgroups of SP2GZ, or rings of integers in SPUPQ. Okay. So this is kind of the name of the game. And let me say, what would we want for a tropicalization? Tropical geometry is a huge story with many, inroads and facets. So I'm kind of not going to give a full introduction to it, but give maybe a rapid-fire introduction to what would we want xtrop to be. So if x is gamma d mod gamma, so if x is a Shimura variety, then we would hope that x trop, the tropicalization of x, would have the following things and following properties. So what is x trop? Well, it's going to be, it is a topological space. It's not, has no structure as a variety or kind of anything else. It's just some nice topological space coming from x, and what's its relationship to x? So it should realize the top weight or weight zero cohomology of x. And by that I mean, this is a canonical quotient of cohomology, this is a sub. A priori, these are not cohomology groups of any nice thing that lies around, but I want to say whatever topological space this is, when I take the homology of x trop, it computes these groups on the nodes. So it's somehow a geometric realization of that. Secondly, x trop should be stratified, or maybe filtered, ideally by symmetric spaces. So somehow we don't want just any space, we want something that actually gives us traction to do computations and have structure, and so that's going to come from having some stratification here. In particular, anytime a space comes with a stratification or a filtration, you should be screaming in your head that there is some spectral sequence computing its cohomology. And so if I have this filtration, it somehow says the cohomology, there's some spectral sequence computing the cohomology of my space x, trop, which is the weight zero cohomology of x, coming from some auxiliary pieces we feed into it. And hopefully we can somehow turn the lever of the spectral sequence machine and hope that, you know, things work out.
In part one, are you saying it's like induced by some proper map that induces?
I wish I could say that. We can't say that right now. That's a great question. That's an open problem in general. It's true for MG, thanks to work of Dan, Melody, Soren, and Sam, etc. But for Schmurrer varieties, we don't know this. I just mean the much weaker claim that the homology of H trop is isomorphic as groups. And I'll make these precise with a theorem in a moment, but I'm trying to motivate. So if we fix additional data that I'm going to call sigma, this is going to give X trop, now labeled with sigma, a cell structure in some nice sense. And this in particular is nice because once you have a cell structure, you have a cellular resolution, and so you could try computing things just brute force cells. And if you're me and you like combinatorics, maybe you would hope that the points of X trop have combinatorial meaning, i.e. maybe they come from graphs or matroids or something nice. I will say almost nothing about this last point, but talk to me after if you like combinatorics. So this is what we would like to have the tropicalization of my Schmurrer variety satisfy. And to give you a picture of kind of what should X trop look like, let me draw a toy model of A2 trop. So in A2 trop, I have a cone that's going to be the positive definite cone of 2 by 2 matrices living inside R3, which I'm thinking about the space as being the R3 of 2 by 2 symmetric matrices. So this is some cone that I'm drawing kind of from a weird perspective. And I'm then going to take this cone, and as we heard yesterday, this has an action of GL2Z. And A2 trop should, in essence, look like the quotient of this cone, modulo the action of GL2Z. I have to put a topology on this cone in a way that makes this actually recover these two first points. And to do that, I need to pick some sort of extra data when I'm defining things. So I need to pick essentially a triangulation of this, maybe something that looks kind of like this. Or maybe this is the matrix 1, 0, 0, 0. This is the matrix 0, 0, 0, 1, 1, 1, 1, 1, and so on. So we get all of these cones, and when we look at the topology induced by asking kind of how these cones glue together by the quotient, we're going to get the space A2 trop. So really you should think about these tropical moduli spaces as being built from quotients of spaces by groups that have some nice properties. And also, this looks like a picture that appeared yesterday in 2 different places.
So what does this tell us about the cohomology of
A2?
SP4?
If you were careful, you could completely read off the top weight cohomology of SP4 from this. And the point is, this is going to all fold up. There will be exactly 1 ray, 1 vertex, and 1 2-cell. And so everything should be 0 and weight 0.
Pretty sure you say 0.
Yeah. And that's recover as a result of a GUSA, I believe. And you can also recover A3 with a similar picture, which would recover your beautiful result on A3. The small part of your result for A3.
Mm-hmm.
So, amazingly, this entire blackboard of wants exists in the literature. thanks to Ash, Mumford, Rappaport, and Ty, and then Kemp, Knudsen, Mumford, Sandna, from the 70s, who essentially found a way to construct such a space. That's amazing. It's always lovely when you can just go to the literature and find what you want. The sad thing is, they would not have written it like this, and you're going to parse about 400 pages of math, in which I find it very hard to read. Because what Ash, Mumford, Rappaport, and Ty actually show you how to do is take this variety X, which is not compact, and compactify it in a very nice way. Now, what do I mean by that? I mean they compactify it so it locally looks like a torus inside of a toric variety, whatever that is. But luckily for us, we can extract from their hard work the definition of what X trop should be in a very concrete way, roughly speaking.
Before you get to that, is there a way of seeing like products of elliptic curves in that picture, right? Since they give rise to abelian surfaces.
Great question. So you're essentially, I have not talked too much about it, so I'm going to punt on that question, and you can talk more about it later. But I think, in general, finding the locus of products of elliptic curves inside of AG is an interesting question for sure. It's really
just
only
diagonal matrices.
probably,
Oh, yeah, I guess.
but I have not thought through it. Because that would be a great guess. But okay, so I'm going to restrict myself to some. I'm going to make some minor assumptions here, and that minor assumption is that I'm going to assume that G is of type A, C, or D2 in the Lie classification. Right, so as you saw, these all come from Lie groups, and so you could say, I only want to look at these 3 types, and in fact, the reason I want to do that is because this allows me to describe G as being the space of matrices preserving some Hermitian form. So this implies, yeah.
I'm a little confused because you said that G mod K is Hermitian,
Yes.
but A is SL, and so that'd be that's not Hermitian.
So
And I don't think about D, so I don't know what it is, but A, I'm sure, is never Hermitian.
that's a very good point.
Except maybe, let's see, SL2R mod. SL
Yes.
is the
So, I mean, I think-
upper half plane.
Did I have my definition on? So it's a good objection, and for me, type A would just be the third case of an SU PQ of an imaginary quadratic root. So I essentially mean, I'm in the case of AG, APQ, or
Oh, I see, maybe it's.
I think it's slightly different. I think there's a. This is somehow from the classification of Hermitian domains that I will not be able to reproduce on the fly, but maybe we can talk. So from this, the point is that we get there exists some vector space V with a Hermitian form J such that G is equal to the set of matrices in kind of SL V tensor such that preserves the form J. So somehow I want to be in the case that I was always in before, where I can talk about having some ambient vector space and some Hermitian form. And the reason I want to do that is because given the data of a Shimura variety. So we're going to define a category, W, G, D, gamma, in these cases. And it's going to depend on the choice of V and J from this, and any other choice would give an isomorphic category. So the objects here are going to be subspaces, V inside of W, that's isotropic with respect to J. I'm looking at spaces on which the form J vanishes. And the morphisms are going to be labeled. We'll have one morphism from W1 to W2, labeled gamma. For all gamma in my group, such that the element of my arithmetic group takes W1 into W2. So somehow I'm looking at all the possible isotropic subspaces, and I'm labeling by all the different ways my particular arithmetic subgroup maps one isotropic subspace into the other. And I don't like making choices, so, you know, I'm not going to make any choice. If you want, you could take some skeleton and talk about the poset of spaces mod the symplectic group. Okay, so with this, we can finally give a definition of a tropical Lyrian variety, or a tropical Shimura variety. And so the definition the tropicalization of X, so the mod gamma, is the geometric realization of a functor sigma that goes from the category W of G, D gamma. And I want this functor to land in the category of rational polyhedral fans. So on the right-hand side here, rational polyhedral fans is the category whose objects are vector space plus rational polyhedral fans, so collections of cones that meet in a nice way. The morphisms are morphisms of vector spaces that take one cone into the other, preserving face structure. And so the idea behind a tropicalization is you have to pick such a functor. It needs to satisfy some compatibility conditions. And when you take the geometric realization of this functor, you should get a topological space that exactly has these properties. And so instead of spending time describing what this compatibility condition is, let me just give you a toy sketch of what the tropicalization actually looks like.
Sorry, can you say again what RPF?
Yeah, so this is the category of rational polyhedral fans.
Thank you.
So it's a vector space together with a collection of cones inside of it, such that faces meet, things only meet along faces, and it's kind of the normal, nice combinatorial cone axioms.
Does this sigma repackage the data that goes into the choice of a toroidal compactification?
Yes. So this sigma is exactly repackaging the data you need for a toroidal compactification of it. In fact, it's phrased entirely in terms of linear algebra, but essentially this is the category of rational boundary components of a Shimura variety, and somehow the sigma is giving you a choice of decomposition at each cone. So what does this actually look like in practice? So we're starting, with a bunch of vector spaces, W1, W2, W3, W4, W5, and maybe I have some arrows between them. This is my category script W. Who knows what it looks like? I certainly don't. To me, it's a very mysterious thing. I'm sure to many of you it's not. It turns out that to each one of these vector spaces here, we can associate a different vector space in a cone. So we get a C of W3, a cone living in an alternative vector space that we call HW3. So this cone lives in a different vector space. It's not W3 itself. And this carries an action of a group, gamma W3, that acts on this cone here. The picture should be that on each one of these vertices, you have some cone living in its own little vector space. And the compatibility condition is I'm picking rational polyhedral fans that live inside of each of these little cones sitting above them, and they have to glue together appropriately. So the choice of what am I kind of decomposing? I'm decomposing the cones over each of these things, and the compatibility conditions are exactly that. My rational polyhedral fans need to lie in the cones that lie over each one of these points. And what are these cones exactly? In the case of AG, they're exactly going to be the positive definite cone. In the case of AG with level structures, it's also the positive definite cone. In the case of the special unitary group, it's going to be a positive definite cone inside the space of Hermitian matrices in E. So somehow they're always looking the same. They always look like positive definite cones. And so with all of this setup and on the thing you might want, which is somehow in this setup you exactly get everything you would want. So to the very long list of co-authors. So, in some sense, this definition depends on the choice of sigma, but the first point is X trop is independent of sigma, at least up to homeomorphism. Secondly, if you look at the weight zero compactly supported cohomology of X, this is exactly isomorphic to the compactly supported cohomology of X trop. Alternatively, if you wanted to look at the top graded piece, X, you could alternatively just take the broad morphology of trop. essentially the compact support or the Brell-Moore is just a way to get around having to take links. So essentially, this says this space is nicely defined and is independent of thing. It computes exactly what we want, and the thing I'll end on is that point 2, there is a filtration on X-trop coming from dimension filtration on the category of isotropic subspaces W. And so once you have this, this means we have a spectral sequence whose EP, whose first page, you could either think as being, let's see, we can call it Brell-Moore homology in degree P plus Q of this cone CW, Q coefficient, where this sum is over all W inside of W. So somehow we have a spectral sequence that exactly is kind of coming from the quotients of these codes by these other groups.
Do you mean the dimension of W is P there?
Yes, I want the degree P piece, yeah. And this is going to exactly converge to the Brell-Moore homology of the top weight cohomology Q. So somehow this spectral sequence will exactly compute the thing we want. So the name of the game now becomes to kind of extract what can you say about these groups gamma, W, CW, and the spectral sequence, or alternatively the cellular resolution that comes from them to actually say things in the 3 cases I said before. But I'm out of time, so I'll end it here, and thank you all for listening.
Questions for Juliet?
Can you say something about the combinatorial meaning
Of these spaces?
Yes.
So for AG, yes, they're what we call tropical abelian varieties, which essentially is a real torus, together with the choice of a positive semi-definite form whose kernel is defined over the rational numbers. If we're doing AG with level structure, you can enrich this to have a tropical abelian variety, so a real torus together with a positive semi-definite quadratic form, some conditions, together with a marking of the M torsion in some nice way. If you're in general for a Shimura variety, we have no idea how to get combinatorial meaning to the objects.
Can you shortly give some examples for the, like at least for one of them?
Yeah,
in
so-
the beginning?
Yeah, so what would be an example? So I'd say an example that I'm quite fond of is that if you look at the case of AG with level M structure, it turns out that the spectral sequence you get here on the E1 page is quite nice. So the E1 PQ spectral sequence is exactly going to be H P plus 1 choose 2 minus P minus Q, I believe, of GLP ZM with Q or coefficients.
Q or?
So So the orientation coefficients. So take them to be Q if you would like. So the
Or you
orientation.
can eat that if m is bigger than 2, right?
Uh,
Then the determinant is automatically 1 if m is bigger than.
Yeah, so if you want to say m bigger than 2, get rid of q or and just take q. Direct sum the number of isotropic subspaces in q to the 2g, dimension p, my FP2G z. There's some number of isotropic subspaces that come out of this. And this is exactly converging to the cohomology of, say, AGM. And this is quite nice because if you stare at this long enough, you see that because you have some quadratically growing exponent, there's a large region in which the spectral sequence is 0. And so you actually can compute a linear portion of the spectral sequence on the nose. I'm happy to say more about that during coffee if people would like.
I think we don't have time for more questions. Let's thank the speaker again and resume.